तो बच्चों आज हम लोग गॉसेस थ्योरम के एप्लीकेशन पे बात करेंगे। पिछले क्लास में हम लोगों ने बताया था कि ये गॉसेस थ्योरम क्या है। तो मैंने कहा था गॉसेस थ्योरम में कि अगर ये कोई क्लोज सरफेस है और इसमें Q1, Q2 माइनस Q3, Q4 और बाहर की तरफ Q5 और Q6 ये चार्जेस हैं, तो टोटल इलेक्ट्रिक फ्लक्स का वैल्यू था E डॉट ds, ये आपके टोटल चार्ज बाई एप्सिलॉन नॉट के बराबर है। तो अकॉर्डिंग टू गॉसेस थ्योरम द टोटल इलेक्ट्रिक फ्लक्स ओवर एनी क्लोज सरफेस इज 1 by epsilon naught times the total charge enclosed by the surface। यहाँ एक बात और मैंने बताई थी कि when you consider this electric field, the electric field of course in calculation of E dot ds is due to Q1, Q2, Q3, Q4, Q6, Q5 due to all the charges, but we get flux only due to charges enclosed by the surface. So this is your Gauss's theorem. Now we can have so many uses of Gauss's theorem। मैंने Gauss's theorem की मदद से कूलम्स लॉ को डिराइव किया था ऐसे कि सपोज दिस इज योर चार्ज Q1 and at this point there is a charge Q2। Now we take a spherical Gaussian surface and apply Gauss's theorem, and the Gauss's theorem is E dot ds at this spherical surface is Q1 by epsilon naught। So here the electric field is directed radially outward, and due to a spherical symmetry the value of electric field at the surface of a sphere is constant। So mod E ds cos 0 is Q1 by epsilon naught, is constant, so it is taken out of the integration sign, and this is Q1 by epsilon naught। So this is E, and the integration of this surface over whole area is 4 pi r square, and this is Q by epsilon naught। So the electric field is Q1 4 pi epsilon naught r square due to the charge Q1, and at this point if the value of electric field is E, the force on Q2, force on Q2 is E Q2, and it is 1 upon 4 pi epsilon naught Q1 Q2 by r square। So this is Coulomb's law, which has been derived from Gauss's theorem। So we can of course calculate Coulomb's law from Gauss's theorem and Gauss's theorem from Coulomb's law। Now if some charge is given to a conductor, we can prove that the charge given to a conductor will reside on the surface of the conductor. This is your conductor. So now what is a conductor? Conductor is an equipotential body. Conductor is an equipotential body. At each and every point of the conductor, the value of electric field is of course 0. Inside the conductor the value of electric field is 0, and each and every point of the conductor is at same potential. There is no potential difference between 2 points on the conductor. Why? Because if there is a potential difference between 2 points of a conductor and also there is a free electron, so the free electron will move from lower to higher potential till the potential is destroyed. So it is not possible that between 2 points of a conductor there is an potential difference, and hence inside the conductor the value of electric field is 0. And if there is an electric field, then the electric field is directed perpendicular to the surface of the conductor. तो ये कंडक्टर के परपेंडिकुलर हमेशा होता है. अब आप कहेंगे कि why the electric field is perpendicular to the surface of the conductor? Because if this is a conductor and electric field is, say, making an angle theta to the normal, then it will have two components. This is the parallel component and this is the perpendicular component. This parallel component will exert a force. This parallel component will exert a force on the free electron, and the free electron will move under this force. But electron can move only when there is a potential difference, and there is no potential difference, so it should not move. And that is why electric field will never have a parallel component, it will have only a perpendicular component. So if there is an electric field on the conductor, it is always directed perpendicular to the conductor. The electric field is always perpendicular to the surface of conductor. The electric field inside the conductor is 0. Inside the conductor is 0. Is 0. No potential difference. No potential difference between 2 points of the conductor. Electric field is always perpendicular to the surface of the conductor. Surface of the conductor, like that. This type of electric field is not possible. This type of E is not possible. Electric field is always perpendicular to the surface of the conductor. So, conductor is an equipotential body. Inside the conductor, the value of electric field is 0, and if electric field exists, it is normal to the surface of conductor. तो ये आपके कंडक्टर का इलेक्ट्रोस्टैटिक डिफिनेशन है कि कंडक्टर इज एन इक्विपोटेंशियल बॉडी. And why it is an equipotential body? Because if there is a potential difference between 2 points on the surface of conductor, the potential difference will be destroyed by the flow of electron from lower potential to higher potential till the potential is destroyed. Now, some charge is given to the conductor. Now, some charge is given to the conductor. Now, we take a Gaussian surface in the form of a sphere. Now, when we calculate Gauss's theorem or applied Gauss's theorem, E dot ds is q by epsilon naught. But inside the conductor, the value of electric field here is 0. So if E dot ds is 0, so charge enclosed is also 0. Charge enclosed in the Gaussian surface is 0. Now we take another Gaussian surface of larger radius, a sphere of larger radius. Here also the value of electric field is 0. So E dot ds is 0, charge enclosed is 0. As long as your Gaussian surface lies inside the conductor, the value of electric field is always 0, E dot ds is 0, so charge enclosed is 0. But we have given the charge to the conductor, so the charge will reside on the surface of the conductor at, of course, 1 or 2 atomic thickness. The charge will remain on the surface of the conductor, and inside the conductor the value of charge is 0. So whenever charge is given to the conductor, the charge will reside on the surface of the conductor. So it has been proved by, of course, with the help of Gauss's theorem, that if some charge is given to the conductor, the charge will reside on the surface of the conductor. Now, with the help of Gauss's theorem, we can calculate the electric field due to a long charge conductor having linear charge density lambda. Lambda is linear charge density. Linear charge density means if the length of the rod is L and Q charge is given, Q by L is called linear charge density. So we are going to calculate the electric field at any point P at a distance R from this long linear charge conductor having charge per unit length lambda. Now we take a Gaussian surface in the form of a cylinder, and the axis of the cylinder lies at the conductor itself. ये जो कंडक्टर है, this conductor lies at the axis of the cylinder, and this point P is the radius of that cylinder. So we are going to calculate the electric field at point P. First, we are going to prove that if there is a infinitely long charge conductor, the value of electric field is always normal to the conductor. The value of electric field is always directed normal to the conductor, as follows. Suppose this is a charge lambda dl. Lambda is the linear charge density, dl is the, of course, charge element. Due to this charge element, the value of electric field is like that, dE. Again, as the conductor is infinitely long, we can get a corresponding charge element, again lambda dl, and due to this, of course, the electric field is like that. And this electric field has component dE, this is theta cos theta, and this is dE sin theta, and this electric field will have component dE cos theta, and this is dE sin theta. The sin theta component will cancel each other, and the only component which is going to survive is dE cos theta, and dE cos theta is perpendicular to the, of course, this line charge कंडक्टर. तो इस लाइन चार्ज पे जो इलेक्ट्रिक फील्ड है वो हमेशा नॉर्मल होता है. Now we have taken a cylinder, and the axis of cylinder is of course the rod itself or the conductor itself. Due to this, the electric field is directed like that. ऐसे इलेक्ट्रिक फील्ड डायरेक्टेड है. इसको हम लोग ऐसे भी देख सकते हैं. सपोज वी हैव अ बुक लाइक दैट. ये दिस इज अ सिलेंडर, this is a cylinder, and the pen is the axis. This is the axis. Now the electric field is normal to the rod, that means normal to the surface of or curved surface of the conductor, like that, like that, like that, like that. So on the curved surface, the outward normal, the electric field, the outward normal and the electric field are parallel to each other, and at this point this is the outward normal and this is the electric field. At this point this is the outward normal and this is the electric field. So the electric field is parallel to the outward normal for the curved surface, and here the electric field and outward normal are perpendicular to each other. Here outward normal and the electric field is perpendicular to each other. So here the flux E dot ds will be 0. Here also the electric flux will be 0, because electric field and area vector normal to the conductor are perpendicular to each other. But on the curved surface, E dot ds is finite. E dot ds is q by epsilon naught. E is E and ds cos 0. Of course, the linear charge follows a cylindrical symmetry. That means due to line charge at each and every point of the cylinder, that means at a distance r, in each and every possible direction, the value of electric field will have same magnitude, and it is directed outward normal, directed in the direction of outward normal. So we can take E, and this is ds is equal to lambda into L by epsilon naught. Lambda is the charge per unit length and L is the length which has been enclosed. So E, and this is 2 pi r lambda into L, 2 pi r L, this is the area of the curved surface. L cell cancel, and the value of electric field is E is equal to lambda 2 pi epsilon naught r, lambda 2 pi epsilon naught r, and it can be written as 2 lambda 4 pi epsilon naught r, and it can be written as 2 lambda r 4 pi epsilon naught r square. Here r give the direction of electric field, which is of course perpendicular to the curved surface. So we have calculated the value of electric field due to this line charge at point P as E is equal to 1 upon 4 pi epsilon naught 2 lambda of course r by r square. In the similar fashion, we can calculate the value of electric field due to, of course, a large sheet. We can calculate the value of electric field due to a large infinite sheet having surface charge density sigma. It may be a conducting sheet or it may be a non-conducting sheet also. Whether it is conducting or it is non-conducting, we can calculate the value of electric field due to infinitely long sheet having surface charge density sigma as follows. This is a sheet. Now, this sheet is infinitely long. And we are to calculate the value of electric field at this point. This is non-conducting sheet. And this is conducting sheet. Now, we take a pill box. Pill box is a small cylinder. Pill box is a small cylinder which pierces into this infinite surface. Half of the pill box is out and half is, of course, in another side. If this is your infinite sheet, there is a cylinder. Half of the cylinder is this side and half is, of course, on opposite side. It pierces into. The cross-sectional area of the cylinder is, say, S. We have already proved that for infinitely long sheet or infinitely long linear charge, the value of electric field is perpendicular to the surface. So the electric field is like that. So for this surface, E dot ds is mod E mod ds cos 0, and it is E into S. For this surface also it is E into S, but for the curved surface, outward normal is like that and electric field is like that. So for curved surface, the E and N are perpendicular to each other. And that is why E dot ds is 0. So here E dot ds is E into S, here it is E into S, and for curved surface E dot ds is 0. So now E dot ds for the closed total surface is sigma multiplied by S. If it is non-conducting sheet, then the charge will reside only on that surface in which it has been given. तो चार्ज ऑफ कोर्स उसी शीट पे होगा जहां उसको दिया गया है. तो E into S दो बार, E into S, and of course it is sigma into S. So S is cancelled. The value of electric field is E is equal to sigma by 2 epsilon naught if it is a non-conducting sheet. If it is conducting sheet, for non-conducting सो ये तो नॉन कंडक्टिंग के लिए था। अब कंडक्टिंग शीट अगर है तो देखिए इस जगह आप लेंगे तो अगेन दो बातें आएंगी। दिस इज योर curved surface and this is your क्रॉस सेक्शनल एरिया। तो ये जो क्रॉस सेक्शनल एरिया है S, इसके लिए आपने देखा कि E एंड S दोनों पैरेलल हैं, तो हियर इट इज E into S, अगेन हियर इट इज E into S, एंड फॉर कर्व सरफेस इट इज 0। कर्व सरफेस के लिए क्या हो जाएगा 0। लेकिन अगर ये कंडक्टिंग शीट है, आप चार्ज देते हैं तो चार्ज इधर और उधर दोनों ही तरफ जाएगा, इसलिए यहां पे चार्ज का जो वैल्यू होगा वो हो जाएगा E into S मल्टीप्लाइड बाई 2 टोटल फ्लक्स। इसको लिखेंगे E डॉट ds इज इक्वल टू टोटल चार्ज बाई एप्सिलॉन नॉट। सो यहां हो जाएगा 2ES and it is sigma multiplied by S multiplied by both side epsilon naught। S से S कैंसिल हो गया, 2 से 2 कैंसिल हो जाएगा, इलेक्ट्रिक फील्ड का वैल्यू हो जाएगा सिग्मा बाई ऑफ कोर्स एप्सिलॉन नॉट। तो कंडक्टिंग शीट के लिए इलेक्ट्रिक फील्ड का वैल्यू होता है सिग्मा बाई एप्सिलॉन नॉट। नॉन कंडक्टिंग शीट के लिए इलेक्ट्रिक फील्ड का वैल्यू हो जाता है सिग्मा बाई 2 एप्सिलॉन नॉट। तो ये मैंने, अब कभी कभी देखिए स्टूडेंट्स को धोखा हो जाता है कि मैंने अगर Q चार्ज दिया एक बार कंडक्टिंग को और दूसरे बार नॉन कंडक्टिंग को, मोस्ट ऑफ द टाइम स्टूडेंट ये कहेंगे कि द वैल्यू ऑफ इलेक्ट्रिक फील्ड विल बी मोर इन द केस ऑफ कंडक्टिंग शीट। कंडक्टिंग शीट के लिए ऑफ कोर्स वैल्यू ऑफ इलेक्ट्रिक फील्ड ज़्यादा होगा, ऐसा धोखा होता है। लेकिन इन बोथ द केसेस द वैल्यू ऑफ इलेक्ट्रिक फील्ड इज सेम। फॉर एग्जांपल दिस इज नॉन कंडक्टिंग, आपने Q चार्ज दिया, सिग्मा का वैल्यू हो जाएगा Q बाई A, बिकॉज चार्ज विल रिसाइड्स ओनली ऑन वन साइड ऑफ द कंडक्टर, एंड द वैल्यू ऑफ इलेक्ट्रिक फील्ड विल बी E is equal to sigma by 2 epsilon naught Q by A 2 epsilon naught. So the electric field is Q by 2 A epsilon naught for non-conducting. If it is conducting and given a charge Q, here the sigma will be Q by 2A, because charge will go on both sides of the conductor, and the electric field is sigma by epsilon naught, sigma by epsilon naught. So here the electric field is Q by 2A epsilon naught. Here also the value of electric field is same. So whether it is conducting or it is non-conducting, if some charge Q is given to the conductor, the value of electric field in both the cases will be same, Q by A epsilon naught. For today this is enough. अगले लेक्चर में हम लोग गॉसेस थ्योरम के कुछ और एप्लीकेशंस यूज करेंगे। थैंक यू फॉर viewing and wait for my next lecture. Thank you, best of luck.